With op-amp circuit analysis, we are asked to find the input and output relationship for a given circuit configuration. An op-amp circuit analysis problem has a unique answer. In op-amp circuit design, we are given an equation or block diagram representation of a signal processing function and asked to devise a circuit configuration that implements the desired function. Circuit design can be accomplished by interconnecting the amplifier, summer, and subtractor building blocks discussed in earlier videos. The design process is greatly simplified by the nearly one-to-one correspondence between the op-amp circuits and the elements in a block diagram. However, a design problem may have a unique answer, since often there are several op-amp circuits that meet the design objective. Now we're going to illustrate some examples to show how the design process is conducted. So here's a design example in which we have an interface circuit, and we're asked that this source, this 5-volt source with a 50 ohm source resistance, delivers 200 milliwatts to this 500 ohm load. So the maximum power available from the 5-volt source is given by the following formula, where we know that P max is equal to VT squared over 2. That's because half of the voltage, in order to deliver maximum power at the input of this interface circuit, half of the voltage is across here. And that's shown in an earlier video, divided by 1 over R. And this calculation turns out to be 5 squared for the voltage source. 2 squared is 4 times the 50 ohm source resistance is equal to 125 milliwatts, which is less than the 200 milliwatt output that we need. What this means is that the interface circuit must contain an active device that provides voltage gain. Now, to determine that required voltage gain, we express the output power as follows. We have P2, our output power, is V2 squared over 500 is equal to 0.2 watts. From this equation, we see that V2 is equal to plus or minus 0.2 watts, the square root of 0.2 watts times 500 ohms, which gives us plus or minus 10 volts. So since the input is 5 volts and the output is 10 volts, therefore we need an overall gain of K plus or minus 2. Now we can get these gains using either the inverting or the non-inverting amplifier. Here in circuit 1 is the non-inverting amplifier, and here in circuit 2 is the inverting amplifier. Let's do the non-inverting amplifier shown here. This figure has very high input resistance, so therefore the current I1 is equal to 0, and we get a gain of plus 2. So for our non-inverting amplifier, once again, we have a gain of K of 1 plus R1 over R2. Now we need an overall gain of either plus or minus 2. Since this is a non-inverting gain, we have a gain of 2. And selecting R1 to be 10K and R2 equal 10K gives us a ratio of R1 over R2 of 1. 1 plus 1 is 2, and therefore our overall gain is 2. Now we can make a lot of choices associated with R1 and R2. So we can have varying values. Now for the inverting case, we need a gain of negative 2. And here the inverting amplifier shown in this figure has an input resistance of R3. We note that the input current is not 0, therefore V1 is equal to 5 minus 50I1, where I1 again is shown here for this inverting circuit. We also have I2 at the output shown here. So when we have that, we get V1 equals 5 minus 50I1. From there, we know that it's also less than 5 volts. So in other words, the interface circuit loads the input source. Now, however, if we define that R3 to be much greater than 50 ohms, then the effect of loading can be ignored, and then we can say that I1 is approximately equals 0, and that the input voltage V1 is approximately equal to 5 volts. With that in effect, we can neglect the effect of loading, and the voltage gain of K equal to minus 2 requires that R4 divided by R3 equals 2, and we note that the gain K equal negative 2 implies that R4 divided by R3, and we can choose that R3 to be 25K, which is much greater than 50 ohms, and therefore R4 must be equal to 50 kilo ohms. So that completes the design. Again, we don't have the effects of loading for the non-inverting circuit, and we have the effects of loading to be considered. In order to choose a resistor properly, we need to be much greater than 50 ohms, so we can ignore the effects of loading. So that's our example in this case of interface design.